Welcome to our class. Today we want to continue with our revision or our study on writing circuits in Noir. This time again looking at the zero knowledge proofs with the Noir and Solidity. So we'll be combining these two in today's lesson. So the objectives of our class today is that we will introduce the concept of zero knowledge proofs using Noir, and then demonstrate this using quadratic equation proof. So we have ax squared plus bx plus c is equals to d, where a, b, c, d are constants. And x is, in this case, a, b, c, d will be public inputs, while x will be private. So, of course, that is what we are doing, zero knowledge proof. So we want to demonstrate, the prover wants to demonstrate the verifier that he knows an x without necessarily revealing what x is. But the verifier will be exposed to ABCD, and the prover also knows what ABCD are. But in addition, the prover knows an x. The x here is a private input, the private witness. So the other, our other target or objective is to integrate our proof into a Solidity smart contract for on-chain verification. So at the end of this lesson, you should be able to do that. And then provide a step-by-step instruction for compiling, proving, and verifying. So these are our objectives. So we'll just move step by step until we get all the steps. And at the end of the lesson, you should be able to verify, to have all these objectives with you. Should be able to demonstrate. So if you are given, you should be able to write a circuit in Noir, and then do zero knowledge proof, and then after that integrate your proof into a Solidity smart contract for on-chain verification. So that is what you should be able. So I'll just give this small example, but then you can always customize it or apply the knowledge we learn into other areas of zero knowledge proofs in Noir. Now, so for our circuit, our today's circuit, this is what will be the structure. So the structure of our project today will be one, would have, this is the title of our project. We call it ZK linear check. This is just a name, just give it a name. But of course, every time you're giving it a name, it's supposed to be a name that is related to your circuit. Yes, but mine is not related to the circuit. I think I used a different name, and the circuit is different. But now inside the circuit, we would have a folder for circuits. Inside this folder would have nagotomil, prover.tomil, src with the main.nr, then the target. Of course, we know what the target will be doing and how it will be generated. Now, so this is a folder. The other folder will be the JS. This is the proof generation, where we have the proof generation scripts inside this JS. Now, so what is important to us inside the JS will be the generate proof .ts and the package.json. Of course, these are not the only things inside the JS. When we begin writing, you see what other contents will be here. inside the JS that will be working hand in hand with this tool that I've mentioned to generate the proof. And then after that, we would have the contract here. It's another folder. And this is where we have the Solidity verifier, verifier.sol. And then we would have the verifier.sol app. I've called it Cyprian verifier app.sol. So again, this will be working together. Get us contracts. Of course, something I want to mention about the circuits here. The circuit will have build.sh, and it will be assisting us in ensuring that some processes are automated. So we'll be automating some processes here and there, and we'll be seeing what it is. Now, so the structure above would just separates the following. We would have the circuit, and the circuit will have to contain what is to be proven. Then we'll have the proven logic. This is our JS, proof chain proof generation. Then we'll have the verifier contract. This is the on-chain validation. So we have these three, and the other ones I've just showed you here. We have this circuit, and we have this JS for proof generation of chain, and then we have this. This one is for on-chain validation of the proof. Good. So let's look at the circuit, and of course I'll be sharing my VS Code, just with this code already inside, and so will just be running. So if you have your WSL, you can just open a new circuit, a new project. You go to where you always store your projects. For me, I always store my projects inside WSL. I store it inside the Rust programs. So just cd Rust programs. That if that is where you usually store your programs, press enter. Once you've done that, later on you'll now make directory. And give it a name. Let's maybe call it Noir ZK proof. Let's call it that. But of course, I said the name of your repo should be related to your repo. That's better. Now press enter, and so after that, that will do. Maybe you'll see a text saying that the project has been created, something like that. But if not, you can now, after that, you can say Nago initialize, press enter. Okay, so that, okay, I think that is when you get that the project has been. So before you do this, you see, after making this directory, you're supposed to cd it, get inside it. So supposed to cd now, if that is the name of your directory, ZK proof. CD that. Then after cding this, now say Nago init. Now, so that means your project has been created, and it's called Noir ZK proof. It has SRC. It has. Oh, when you do that, of course, when you do the way I've done, Circuits is not there. Circuits is not there. Circuits is not there. So if you do the way I've done, it means you'll have to open it and then make directory circuits. Make directory circuits and move your Nago TOML and the SRC inside the circuits. But if you want to avoid that, if you want to avoid that, let me just take you back. You said make a directory and you gave it a name. Give it a name. What was your name? Noir ZK proof. Okay, after that, CD Noir ZK proof. After CD that, you can say make directory circuits. Okay, this is now okay. Then after that, CD circuits. After CD circuits, you can now say Nago finish. So this is now okay. This now will give you circuits. Otherwise, the earlier one, you would have created circuits. Then you see the other one, we had already skipped that. We had already skipped that, but in our project, we said we need it. And we had already skipped it. So when you skip it, it means you'll have to create it later and then move the rest of the contents that we had already created inside the circuits. But to avoid all that, you would just use this process. You would use this process. Okay, so let me just open my VS Code. Okay, WSL, and then I show you the steps you just described. And then after that, we proceed. Of course, once you do Nago init, you now say code, you say code. Just again show you that. You say code, then space and dot, and then press enter. That will open for you the VS Code, and then you copy this and insert and paste inside. Paste inside your main.nar. Okay, so let me share my WSL so that I show you, just do the steps I've just said together, that you understand them. Okay, so this is my I'd say that you would first of all get into where you usually store your programs. For me, store it inside Rust programs. So I see the Rust programs. After that, we say that we wanted to make directory, and we wanted to call it Noir ZK proof. Let me just call it proof 2, supposing I have another one. The same name, I want to avoid that. We call it Noir ZK proof 2. Okay, let me now get inside of this project, CD Noir ZK proof 2. Good. After that, we already said we have want to have our circuits ready. So make a directory, circuits, then get inside CD circuits. Good. Once you're there, it will say Nago initialize. Okay, so I think mine is saying that because my Nago is not in my path. So first of all, let me see. I want first of all put it in the right path. So this just submit. There's a command I'm supposed to use just to ensure that my Nago is in the right path, so that when I say Nago inish, it is supposed to understand the command. But for you, if your Nago is well installed, so what this means to me is that my Nago is not well installed, or I have not defined my path correctly for Nago. But if yours is already well installed and well defined, you don't need to go through all this. But for me, mine, from the command, from what I've just seen, my Nago is not well. So I use this command echo, export path, and so on. Let me see if it will be the right. Okay, so let me now again repeat it. I think my Nago is now in the right path. My Nago is now in the right path. So let me do that. Good. It's in the right path. You can see when I said Nago Inish, it has now said the project successfully created is located at home Cyprian Rust programs, and it's called Noir ZK Proof 2, and we have circuits inside. Good. Now, so what I want now to do is to open this, open what the project we've just created. We say we just use code space and then a dot. Now, when I press enter, it opens for me the VS Code. And let me just show you the VS Code on my end. One that it has just opened on my end. And here it is. You can see we have circuits here. We have the SRS. Inside SRS, we have main.nr. This code is what we will replace by the one I just showed in my PDF notes. We have the number terminal here, and it has all this. Now, so you have these circuits. Now, next time we will want to create another folder we call, let me say, another folder was JS. We'll just come here and say new folder and call it JS. And if you want another folder again, and this other folder, suppose you want to call it, contract, again, say new folder and call it contract. So these are the folders. You have circuits, but now the problem here is that our circuit now appears like the project. It appears like a project is called circuits. This is what it appears here. And this was not my intention. I did not want my circuit to be called, the project be called circuit. The project was to be called, okay, I've seen what I've done. I've seen what I've done. Okay, just delete this first of all, and I'll take you back. And then delete this again, and I'll take you back. Good. I've seen what I've done. Let's just go back. Let's just go back. Oh, I was wondering why it was called something different. So let's just come back here. Let's come back here. Now, we did code a space dot inside circuits. That is not correct. We need to, first of all, come out of circuits. First of all, we need to come out of circuits, then go to the main root. When we are inside the main root, we will have said now code, then dot inside the main root, so that now it opens for us the correct project. Good. Let me now share the correct one, the one that it has just opened. Yeah, that is a procedure. We need to first of all get out of circuits before we do, so that we are inside the main root. You can see now this is now different, and this is what we wanted. This is what we wanted. We wanted our project to be called Noir ZK proof. You can see the name here. And then inside that, we wanted to have circuits. And then now we want to create other folders. And the other folder we want to create is JS. You can see that is correct. And again, we want to create another folder again and call it contract. That's how it's supposed to be. Now, but circuits we already have, let's just check what is inside. Inside circuits, we have the SRS and then we have the Nango terminal. But what do we have inside SRS? We have the main.nr, and this is what we'll now be replacing by the code I had shared in my circuit, in my PDF. This one will be replacing. Okay, so let me now continue to my PDF, and then we'll come back again to making more, now copying our codes and pasting them here. So just seeing how to come up with a new project and how to add folders that we require later on. Now, so once you have that, take this circuit here and paste this inside your main.nr. Now, so we need to understand what our main function talks about, and we've already done this before, so we just trying to emphasize. Okay. Now, what you see from our function, you can see that X is private, A is public, B is public, and C is public, D is public. You can see we show which is public by the use of the word pub. So the word pub here means that the element there is public. But you can see there was no pub here, so it means X is private. Now, because what we want to prove is knowledge of X such that A raised A multiplied by X squared plus B multiplied by X plus C will give us D. So we would then assert, this is just to ensure that our circuit behaves correctly, and to assert that the left side equals the right side, and to assert that this left side, and we're calling the left side to be mx squared plus bx plus c is the left side. We want to assert that this left side equals to d. So we want to assert. So you just copy that, and after copying that, you paste it inside your main.nr. Okay. So I think I should now share my code so that we move together, because I know you've already pasted yours. Okay, here is mine. My main.nr is this, and that is what we wanted to just replace. And I've just replaced mine. Now, after replacing, let me look for my terminal so that we can do Nago compile and just see whether it's compiling properly. And for Nago compile, you would go inside circuits, because that is where our Nago terminal is. So CD circuits. Then after that, you can say Nago compile, Nago compile. It has compiled properly, and after that, you can see that we now have a new folder, a new file called target, new folder called target. And inside that, this target is inside circuits. And inside target, we now have circuits.json. Okay. Now, we can also try to do Nago execute, but before that, let's get our Nago, no prover.toml. So we do Nago check. And you can see that when we did Nago check, we got another folder called prover.toml, and it's asking us to add in a few things. It's asking us to say what A is, say what B is, say what C is, say what D is, and so on. And then what X is, asking for all those. So you just give it those values, but they should make sense. It should give you D. So for instance, if A is 3, B is 4, D, C is 5, then D will be 25. Because what we are doing, we are saying 3 multiplied by x squared. X squared is 4. So 3 multiplied by 4. Then we are adding b multiplied by x. B multiplied by x. And then we are adding c. Should give us d. So you can see this first one is 12 plus 8, that is 20, then 25. That is why D is 25. So this is correct. So if it's correct like that, when you now say Nago execute, it should now run. Nago execute. Good, it has now run and it has told us something that the circuit witness successfully solved, and that it's saved inside target. It's saved as circuit.js, inside target, circuit.js. This is our witness. Witness is stored here. Good. Good, very good. Now, so let's come back to our main.nr. You may want to just verify that your main function is working correctly. And for you to do that, you need to add tests, unit tests. Unit tests will assist us to verify if our main function is behaving as expected. Otherwise, you can write a function that will not be working as you expect it to work. So for us just to be sure, we need to add more tests, negative, positive, and even boundary tests, just to see whether it's working. So I've added some tests here. The first test, I want my A to be 3, B to be 4, C to be 5, and then is it true that D will be 25 if X is 2? And so if anything is wrong, it will not compile. Okay. But this one, the last two, these ones are expected to fail because you can see I've maintained the same values of A, B, C, and I've changed X. X is now 3, and this should fail because when X is 3, D will not be 25. D will not be 25. So that means it will fail. What about this? Now, X is 2, but I've changed some values here. I've even maintained A, B, but we changed C. But now again, when you change C to 10, D will not be 25. So it means these values again are not correct. So for it to pass, I have to include should fail inside bracket like this, should fail. But if I remove should fail, then it fails. Okay, so let's do a test just to see that our tests are running properly. It says running 3 test functions, and then it says that the test test invalid equation is okay. Test valid solution is okay. Test invalid solution is okay. So we had 3 tests, and those are what I would call them. That is how we call them. This one is the first one there. Test invalid equation parameters. This is this. And it says it's okay. Then the second one was the function is test invalid solution wrong x is here. And then lastly, we had a test valid solution, and is here, and it says it's okay. So what I was saying is, you see, for this test here, the values given for x, a, b, c, if you do the computation, the result, and even for x, if you do the computation, the result is 25. And for this one, when you do the computation, when you do qx squared plus bx plus c, the result will not be 25. So for us to have it not panic, we use should fail. But if I remove this should fail, if I remove should fail and again do NAGO test, then it panics. You can see 2 tests have passed and 1 has failed. 1 has failed. So this test has failed because those values, when you do the computation, they don't give you 25. And we've said they are supposed to give us 25, which is not correct. So for it to pass without this panic, you just return that should fail part. Return that. Good. I have returned, and you can see now it passes. Now we want to automate the process of generating proof, not generating proof, verify.sol, and then the process of compiling, and yes. So for us to automate that, we need to come up with the build.sh. Build.sh. So I'm sharing okay, this one I'd already done it. It's the same circuit I've been talking about, the same thing, but this one I'd already done it. Just delete this target. Now, this is my build.sh. It's a script that would automatically generate what you want it to generate. In our case, we wanted to, first of all, do compiling of the circuit. It should supposed to do NAGO compile for us. that we are not doing it manually. We are not doing Nago compile manually, but we just running the script. When you run the script, the circuit is supposed to be compiled. Now, if the compiling fails, it's supposed to tell us circuit compilation failed. Now, after circuit compiling, it's supposed to generate verification key. We want it to generate verification key that we'll be using in our proofs, creating our proofs. Now, the command that I wanted to use to generate verification key is here. It's up to here. There's a command. Now, after generating verification key, it will store it inside our target. That's what you're seeing. That's why it's storing it inside our target. And the name of that would just be VK, write VK, the verification key. And for you to create this verification key, you want to use okay, so for me, first of all, let me just come back. I changed the name of my project. I changed it from circuits to coming here. I changed it to Noir Solidity Verifier, a demo. That is what I changed the name of the project to be. So when you do Nago compile, then you come up with the Noir Solidity Verifier demo.json. And this is what is used in creating the verification key. This is what is used in creating the verification key. That is what you are seeing here, that we're using Noir Solidity Verifier demo.json. To create a verification key, and after creating that verification key, storing it inside target. Now, so our build.sh is inside our circuits. So let's just do that. Let's get inside circuits. Inside circuits. Then let's run it's dot backslash. I think this is forward slash, or is it? Yes. And then build.sh. Now, it just says compiling circuit, generating verification key, schema, ultrasound, and then verification key has been saved inside target as BK, and then generating Solidity verifier contract, and this is also stored inside contract as verified. So first of all, let's come to target. And we can see verification key here. You can also see the process of compilation. When it did compile, it gave us Noir Solidity verified demo.json, and used this therefore to create our VK. Good. Let's come back to build.sh. So that is just one thing that we'll be doing for us to create verification key. The other thing that I wanted to do automatically is to create the verifier.sol. This one will be using it on chain. So create that. And it's using this command. The command is bp write solidity verifier inside target. And of course, you're using verification key VK. And then after writing it, you store it inside contracts as verification, not verified. So if it fails, you tell us. Okay, so let me again delete what we already exists, because when we ran, it was created, and I had not told you that it was going to be created. Let me delete it. The verified sol. Again, I will still delete this target if I want. Still delete it. So our expectation is that we run the script build.sh, and it does the thing for us. Creates the target with it, the content. So just the content that we just deleted. That also creates the verified song. So we are still inside circuits. That is okay. Dot slash build dot sh. Good. You can see verified song has been created here. Let's just scroll it to the bottom and see the type of contract you're dealing with. Home verifier is a base home verifier contracts. This contract home verifier and so on. Now, so you've seen what build.sh can do, and it can do more than this. It depends on the commands you give it. You can give it more commands depending on what you want to auto-generate. Okay. Now, so I think that is okay. That is okay as far as circuits is concerned. So I think we can now proceed to JS and do proof generation. Before that, I can just share my PDF so that we follow it the way it's directing us. So we've already talked about the tests, and you've seen how to do level tests, what the invalid test will be doing, what the valid test will be doing. Okay, so we are now ready to go to JS and do our proof generation. Now, inside our JS, this is our JS. You want to create this folder called generate proof.json.ts. This folder. This file generate proof.ts. That's the name of what we call our project, Noir Solidity verified demo. This is inside our circuits and inside our target. So that one we are importing it. And we're also importing Noir lang, Noir underscore JS. And then very important, our inputs, our constant inputs. Our A was that, B was that, X was that, and so on. Now this, we also want to have package.json. And lastly, we want to have our TS config just now. Don't worry about yarn lock. Yarn lock, you just use yarn install. That is because we want to run yarn generate proof. For you to run yarn generate proof, you require yarn. So when you would first of all do yarn install, and you can see yarn comes with all these cache install and so on, node modules and so on. So those ones you shouldn't worry. For me, I already did that. Now, so what we need to do, you get out of circuits. I'd already shown you how to create JS. You would say make directory JS. You can do that. Or if you want to do that, you will come here and just click new folder and call it JS as we did earlier. Good. So once you're inside the JS, you can inside the JS here. Once you click on the JS here like that, right clicking on it, you have new file, and just this new file, call it the name you want. For our case, we want it called generate proof.ts. So once you have that, you paste this content inside. And then from there, again, you come back here and again, right click and say new file. When you click on that new file, you can now call it package.json. And after that, you can paste this inside. Similarly, come back here and right click, new file, and then that new file, call it tsconfig.json and paste all this. So that's what we'll be doing. That's what we'll be doing. Don't bother about yarn and so on. This one will be the content inside will just come automatically once you say yarn install. Because you would just come here and say yarn space install and press enter. So when that happens, all those yarn come, all those yarns will be installed and their content will be intact. Now, after you've done that, let's just get inside the JS. Good, and we want to generate the proof. So say generate proof. And generate proof. Okay, so after some time, it returns. I paste that. I will see it from. You've seen what it was. Okay, yes, this another one. I don't know why I'm getting it from. This is pasted. What I'm interested in is this part. It says proof has been generated successfully. So when you come to target, you should be able to see that proof. Come to target, and here it is. The proof has been generated successfully. It's not the only thing that has come about as a result of yarn generate proof. The other thing is public inputs have come, and our public input, A was a public input, A was 3, and B was 4, you can see that. These are hexadecimal numbers. C was 5, and lastly, D was 25. So 25, when you convert it, 25 is a decimal. So when you convert it to hexadecimal, it will be 19. Convert it to hexadecimal. So what What we are shown here are hexadecimal numbers. These are public inputs. We had A, B, C, D as our public inputs. So they have also been generated here by doing Young generated proof. So therefore, our proof is there. It says the file is not displayed. Now, there are ways you can use to display it or to cut it. There are ways you can use. Let's go, not go into that. What we wanted was a proof. Now, once you have this proof, you want to verify it. So to verify it, you get inside contract. There is a contract. I've stored my commands here, so I'll use forge test optimize to verify. So I run that in my terminal. It does run, and it means that proof has been verified. It says running 5,000 gas report and so on. No files changed, compilation skip. Okay, run one test for test starter.t.sol. Okay. I think I need to mention that before you verify, you need to have the contract folder. The contract folder for us is already here. This is our contract folder here. So inside our contract folder, don't bother about lib. Reasons come automatically when you install Foundry. So the only thing you need to create is the reason you saw how it came automatically when you ran build.sh. So again, you should not bother about this. Okay, so the only thing you need to bother about is this, the app, the Cyprian verifier app.sol, you can call it any name. So the content will be this. Very important about this content is that we define how many public inputs we're expecting. We're expecting 4 public inputs. And that's why I put here that public inputs will be of length 4. There are 4 of them. We're expecting 4 public inputs. That is the most important thing about this. Okay, you can read about many of all of this. And for me, this part is very interesting because supposing I want to change it and want to lie that there are only 3 public inputs, then it will not succeed. Let us try and see if that can be verified. You see, it has failed. It has failed because it was expecting 4 public inputs. What does it say when it fails? It says encountered a total of 1 failing test and 0 succeeded. There was only 1 test, and that 1 test has failed. Okay, so this was a very long output here. So I cannot see all of it. I thought I would see what it wrote at the beginning, but I cannot. It was a very long thing. Oh, yeah, it's here. It's here. It says expected 4 public inputs. In fact, it's expecting 3, 4, 5, and 25. But we have provided, we say we have 3. So it knows that there are supposed to be 4. So it says it's expected 4 public inputs. Okay, so let's just return them. We cannot lie here. Just return them to 4. Good. Back to 4. That is one file that we need to have inside our contract. The other file that we need to have is inside our tests, and it's called starter.t.sol. Now, this one does many things. One, you have again to tell us how many public inputs you expect. In our case, you're expecting 4, and you can see I've listed them here. They're here now. The first public input was 3, then 4, then 5, then 25. All of them listed here. Then I have to say how many. So to me, again, this is a very important circuit, a very important file that we must have. And I've already highlighted the most important bits of this, this file. Now, so if you try to change any of this, then let's just try. This was 3. Let's try and change it to 1. Let's just try and see and say, well, to verify the proof. It does not succeed. It does not succeed. So you cannot lie, actually. You cannot produce a wrong proof at any given time and to present it as a right proof. Except some check failed. Some check failed. So you can't lie. It knows what public inputs we have, that those that will agree with the proof generated. Because the proof has already been generated. So to verify it, the public inputs must just agree. Let's change this again to 2 and see whether it will accept that we have 2 public inputs. It does not accept. It knows there are 4. Let's say that there are 2. It knows there are 4 public inputs. Because the proof has already been generated. So what we're just doing is to verify. Now, that was one way of generating the proof. We did that proof generation by use of yarn generate proof, and we were inside yarn. You remember that yarn is the part that will be generating proofs for us. That is not the only way to generate a proof. Let me again show you another way of generating the proof. Let's get back to circuits. Get back to circuits. Then do nano execute to get a witness. Remember that we had deleted our, so we don't have .gz here. We don't have .gz solidity, Noir solidity verified demo.gz. We don't have it here. That is our witness. Let's just create it. Good. We now have it. Noir Solidity verifier demo.gz. Now, so since we now have it, we can now, without going to JS, we can now again generate a proof. We can generate a proof without going to JS. And the command we'll be using is this BB proof. And we are saying that we are going to use no solidity verifier demo adjustment and create a proof. Also, we'll be using no solidity verifier demo.gz, which is inside our target to get our proof. So we always required to have this inside our target. This one comes as a result of Nago compile, and we also require this that comes as a result of Nago execute. And once you have those inside your target, use this command in the terminal, and the proof is generated. You can see there's a proof here. And again, it has come with public inputs. Remember earlier on, our public inputs were clickable, you could click and see, but now the current proof has just come with these public inputs. You will find if you try to get what is inside here, you will find that it's the same thing that is here. It's the same thing. These public inputs are just the same things here. So again, we've generated a proof. And it says that the public inputs have been generated also and have been stored inside target, and the proof has also been generated and it's stored inside target as proof. So once you generate that proof again, as we did earlier, you can always verify it. But to verify it, you have to again go back to our contract with this command here. Go back to our contract. So just want to go to our contract, CD contract. Oh, first of all, get out of circuits, then CD contracts. Now, so you will find in fact, the output will be the same as the one we got earlier, because we are dealing with the same proofs. We are dealing with the same proofs, so the output will be the same. Good. You know, for you to do this verification, we're using Foundry. For me, I had already installed it. For you, you have not, so you need to install it. Once you install it, you will automatically get the things you're seeing that I have, like this lib, and you don't have. So you install Forge. Install Forge. In this cache, you will have it. You even have this out, and so on. But this one, if you want, you can copy mine. And even this pretty, this one, it came about as a result of installing prettier. I wanted to use prettier just to do formatting of my code so that my code is well aligned. So for you to do that, you need to use prettier. And prettier, when you install it, it comes with this. Now, once you've created your project, you can want to edit your README so that it agrees with what you have as your project. You can edit your README so that it reflects your project. Okay, so we've gone through all the steps, and now you know how to create these projects. You can use the same knowledge to create different projects. So how does the Solidity verifier work? So I've said that the Noir compiler generates a proving key, the verification key. So the proof, which is generated off-chain, as you've seen, would include commitments for the private witness. The Solidity contract, which we call verified sol, would see the proof bytes and the public inputs as we saw. So if the verification succeeds, then it means this equation is guaranteed without revealing X. So you would not have revealed X. So what the verifier would just be seeing will be the proof. Just be the proof, and then verifies the proof. Verifier verifies the proof. And you saw when we tried to verify the proof and tried to change a few things, the verification was not going to succeed. It failed. So you don't need to doubt the proof you're given, even if the proof is coming from the prover. Because if the prover tries to tamper with anything on the proof, and then you can be sure that the verification will not succeed. But if the verification succeeds, then it means that the equation given to you is correct, and that this guy knows what X is without necessarily having to reveal it. You can be convinced he knows what X is. Now, I had already said that you may want to just use the knowledge you've now acquired to do more. So here I just give part of what you can want to venture in. You may want maybe to extend the proof I've just given to cubic equation. For us, we did with the quadratic equation. Now, this cubic equation just increase the constants. A, B, C, D, E, these are the constants, and X would still be private. Okay, you can also extend it to two private inputs. X and Y are being private, where A, B, C, D becomes public, but X and Y being private. Also extend this to cryptographic use cases, such as partisan commitment opening, Poseidon hash pre-image and range proofs, This will be part of where you can apply this knowledge and come up with the proofs. You can also do this in integration by integrating this knowledge into rollups, private payments, and on-chain reputation. So it's just upon you to do more exercise, use the same knowledge in what I've just mentioned here, either in cubic equation, extending to cubic equation, or doing the same equation as we did, but this time around have two private variables, x and y, or use the same knowledge to do cryptographic use cases, such as the range proofs, Sweden, hash pre-image, or partisan commitment opening. Or you can integrate the same knowledge into rollups, private payments, and on-chain reputation. Now, so what is our takeaway? What are we getting away with? What do we understand from this circuit? One, Noir makes writing of ZK circuit simpler and Rust-like. Private inputs stay hidden while proof remains verifiable on-chain. So you can verify this proof on-chain. Public inputs are essential for contract compatibility. And then the quadratic equation we saw, that is circuit, is just a minimal but powerful example. You can always use it, or you can always use the knowledge we just gained to write more powerful circuits. I think that is where I want to end our class today. Just encouraging you to do more exercise, write more circuits, just to make you comfortable and again used to writing circuits. You have to do enough practice. So thank you.